Hello student, today we are going to discuss about semi-empirical. Okay, semi-empirical mass formula, which is a part of paper 9 physics honors. Now Witzika in the year 1935 he expressed the atomic mass of a nuclide, in fact atomic mass of the nuclide, okay, in terms of a series of binding energy correction terms to the main as combination from protons and neutrons. Now the expression is called semi-empirical mass formula or Witzika mass formula. Accordingly the mass, capital M, okay, capital M, the mass of the neutral atom containing Z proton, Z number of protons and N number of neutrons will be given by M, Z comma A is equal to Z into small m subscript P plus A minus Z into small m subscript N minus B by C square. Here B is the binding energy. It consists of series of terms, each representing same general characteristic of nuclei. So what are the terms and how it can be seen or it can be defined? We can just look into it one by one. Number one is volume energy. Now nucleus is a sphere of containing A nucleons. It is a sphere containing A nucleons. These nucleons are held together by a strong attractive force. Therefore reduction in mass of the nucleus should be proportional to A. So the binding energy should be proportional to A, in fact, okay. Now since the volume of the nucleus is proportional to A, therefore this term is referred to as volume energy and is denoted by E subscript V. Volume is equal to minus C subscript volume into A. Here C subscript volume is a constant term, okay. Now the second term is surface energy, okay. Talking about the surface energy, in volume energy term, it is assumed that all nucleons are surrounded by other nucleons. It will be true in case of infinite nuclear matter. But in fact, the nucleons on the surface of the nucleus will be attracted only by the nucleons on the side. Hence, there is a positive surface energy term analogous to surface energy of a liquid drop. This effect gives rise to surface tension in liquid. So the surface energy of the nucleus, is proportional to surface area, okay, which in turn is proportional to the square of the radius, hence A to the power 2 by 3. So what we can say that E surface is equal to C surface subscript A to the power 2 by 3. Here again this C surface is a constant. Then the third part is Coulomb energy, okay. In writing the volume energy terms, the charge of nucleon was ignored. Volume energy term, okay. Actually a nucleus consists of Z protons, okay, and A minus Z neutrons. The proton experience Coulomb's repulsion, hence the binding energy of the proton will be less than that of neutrons. Obviously, the energy due to Coulomb repulsion must be subtracted from the volume energy. So, the Coulomb energy term will be equal to the electrostatic potential energy of Z proton packed together in a spherical symmetrical assembly of mean nuclear radius capital R equal to R naught E to the power 1 by 3. Okay. So, for a spherical volume of uniform charge density, the Coulomb energy is given by E Coulomb is equal to 3 by 5 Z into Z minus 1 E square by 4 pi epsilon naught R. Now what we know is that R is equal to R naught E to the power 1 by 3. Okay. So this term may be expressed as E Coulomb is equal to C Coulomb, okay, Z into Z minus 1 by A to the power 1 by 3. Okay. So for a very large Z, we can write C Coulomb, okay, Z square, right, A to the power minus 1 by 3. This is for large Z. Now number 4 is asymmetric energy. Here it has been observed that for light nuclear, okay, smaller rather, is most favorable or a most favorable stable system, while for heavy nuclei there is excess of neutron over proton. That is what we can say that n is greater than z for a large nucleus. Okay, it has been found that whether n minus z increases or decreases, the nuclei are found to be less stable. So the difference in number of protons and number of neutrons in nuclei causes asymmetric configuration. So the reason for asymmetric configuration is difference in number of protons, okay, number of protons and number of neutrons. Okay, now therefore a term in the binding energy signifying this asymmetric effect must be included. Okay, now for a nucleus of mass number A and atomic number Z, the number of neutrons will be capital N is equal to A minus Z. So this is the number of neutrons. Okay, so excess of neutrons over proton is N minus Z. This causes decrease in binding energy because they are out of reach of the nucleus. Now the fraction of nuclear volume so affected is N minus Z by A. Therefore the net decrease in binding energy is proportional to N minus Z by A into N minus Z, which is equal to N minus Z whole square by A. Therefore the asymmetric binding energy term is expressed as E asymmetric is equal to C asymmetric N minus Z whole square by A. Okay, is equal to, further you can write it like this, A asymmetric A minus 2Z whole square by A. Since this could be obtained because N is equal to A minus Z. So this is again a C symmetric is a constant. Next we have we are having pairing energy, which is number 5, pairing energy. It has been observed that the nuclei containing even number of protons and even number of neutrons, known as even nuclei, are most stable. So even nuclei are most stable. Okay, while those having odd number of protons and odd number of neutrons, known as odd nuclei. Okay, odd nuclei are least stable. The nuclei having even number of protons and odd number of neutrons and vice versa, known as even odd nuclei. So even odd nuclei have intermediate degree of stability. Right. This effect is referred to as pairing effect. So this particular thing is known as pairing effect. Right. This arises mainly from the fact that nucleons tend to pair up, okay, in order to get lowest energy state. It is to be observed that the neutrons and protons have quite different energy state. Obviously this effect causes an increase in the binding energy when both N and Z are even, and decreases in binding energies. Okay, so the pairing energy E pair may be expressed as 0 for odd A, right, minus delta for odd N and odd Z, and plus delta for even N and even Z, right? So it is found empirically that the pairing energy term is delta Az. This could be written as delta as a function of A comma Z is equal to plus minus C pairing A to the power minus 3 by 4. So C to the C subscript pair is the constant. When with all the above correction, okay, the binding energy expression can be written as B is equal to, ultimately including all the 5 points, okay, 5 binding energy things, we write C wall subscript minus C surface e to the power 2 by 3 minus C coulomb Z square e to the power minus 1 by 3 minus C symmetric A minus 2Z, okay, whole square e to the power minus 1 plus minus C pair e to the power minus 3 by 4. Okay, so this is the binding energy expression, okay, the complete binding energy expression. So the semi-empirical mass formula, the first formula which we have mentioned earlier, could be written as capital M as a function of Z comma A is equal to Z subscript MP plus A minus Z M subscript M minus the whole of this B, okay, divided by C square. It could be written over here, okay. This B is can be obtained by from here. So what we can see is that the first formula which we have mentioned over here, we can substitute the value of B from our formula, and this expression is known as Weizsäcker mass formula, okay. But the constant, this C volume, it has been obtained experimentally is 16.11 mega electron volt. C surface, again it is obtained 20.21 mega electron volt. C coulomb, it's around 0.583 mega electron volt, and again C asymmetric is equal to 20.65 mega electron volt, and finally C pair is equal to 33.5 mega electron volt, okay. So these are all these are the constants. Basically it fit the experimental data best as so far we know. So thank you very much. Again we will meet in the next lecture. Thank you.